Welcome to Pavonars, webinars for the pavement community. My name is Andrew Braham, and today we're going to talk about reducing the sample size for cold in-place recycling, design, and testing. So how did this study come about? Well, we had too many buckets, and if you've worked in an asphalt materials laboratory, you know that a lot of our space is dedicated to the storage of buckets. So what we did is we did an experiment that asked the question, can we reduce our sample size to test the material that we need to bring in from the field in order to reduce the amount of buckets that we have so that we can not have to bring as much material from the field into the laboratory. Now this work was done by Alex Jackson. His MS thesis was titled Reducing Sample Size for Cold in Place Recycling, Design and Testing. Alex received his Bachelor of Science in Civil Engineering from the University of Arkansas in 2012, and he received his Master's of Science in Civil Engineering in 2014, also from the University of Arkansas. And his LinkedIn profile can be found below in the comment section. So what is cold in place recycling? Well, let's say that we have our pavement structure here where we have a distressed HMA layer, an old base, and the subgrade. What CIR does is it mills 3 to 6 inches of the distressed bound material, so only the hot mix asphalt layer, and then it injects water, asphalt emulsion, or asphalt foam, and other additives into this new recycled layer. You then compact that layer and place a surface course or some sort of maintenance treatment on top of the CIR. So your new pavement structure is your subgrade and your old base. There could still be some existing HMA layer, but then you have the CIR layer, and on top you have some sort of surface course. There are two different ways that this can be done. One is a cold in place recycling train that has supply trucks, a milling head, screen, crusher, pug mill, and paver, and you can see those on the images on the right. At the very right side of that image, you can see the two supply trucks, followed by the milling head. You then have the screen and crusher and pug mill, and it all goes into a paver at the end of the train. And there are also shorter trains. Here's one that just has a supply truck and a milling head, and then behind this is a pickup machine and a paver. And there's really any sort of variation of equipment out in the field that's possible, and these are just two examples of what you may encounter. But all of these are milling up 3 to 6 inches of bound material and then placing it back down after mixing with either asphalt emulsion, asphalt foam, and other potential additives. Once the material goes through the paver, it comes out the back of the paver. And if you've ever been on a hot mix asphalt job, you can see that this is a little coarser than asphalt concrete. It does not look like an asphalt concrete mat. It looks like a CIR mat. And after this comes out of the back of the paver, you then compact it with a combination of steel wheel rollers, and some of them have the vibratory mode on, and then other passes they do not. It's a static steel wheel roller. And then you also have a pneumatic tire roller. And there's some sort of combination of these steel wheel and pneumatic, and the steel wheel may or may not have the vibrating capabilities. So how do we actually design and test for CIR in the laboratory? Well, we need to take samples of the existing road. And samples of the existing road take lots of buckets of material. This is an example of a shed at the University of Arkansas. Or it can come in the form of cores taken from the pavement. But regardless, this is a lot of material that's required. And this material is required not only for the mix design of CIR, but then also for the performance testing to evaluate different types of additives and stabilizing agents. So our solution is to reduce the sample size. What are different geometric sizes of samples that we could try to test to see if we can quantify the properties of the CIR? So our experimental matrix We had three different testing apparatuses, so we had three different geometries: the IDT, the indirect tensile test, a three-point bend test, and also a torsion bar test, and we call that the DHR in this presentation. We had three different gradations. We had the original gradation, then we essentially cut that gradation in half and then in half again, so we sized down the aggregate particles. We used four different emulsifiers, everything from a fast emulsifier for an asphalt emulsion down to a slow set with a couple in between. We tested at three temperatures, -20, -30, and -10. And then we used two different types of material. We used reclaimed asphalt pavement, or RAP, and then AHTD Class 7 virgin aggregate, now RDOT. And this was a partial factorial, so we weren't able to test all the different levels at all the different combinations, but we did a partial factorial in order to look at all of these variables. So the first test that we run was the indirect tension creep test, and these samples are 150 millimeters in diameter and 40 millimeters thick. They're loaded in compression, and the horizontal and vertical strains are measured there at the center of the sample. And this is the current accepted test method for creep compliance, and it follows AASHTO T322. The next test that we ran was a three-point bend test. These were 150 by 30 by 40 millimeter bars, and we measured the deflection at the midspan of the sample. We calculated the compliance according to the Bernoulli-Euler beam theory, and this test was adapted from a Chinese standard T715, and the version we used was from 1993. Now the benefit to this geometry is it is about 1/4 of the material that's needed for an IDT sample. So if you remember all those buckets, we could reduce those by 25% if we used this sample size instead of the IDT sample size. Now the third piece of equipment, the torsion bar, which we call the DHR, this uses very small sample sizes. They're 12.5 by 12.5 millimeter samples. The tests of these samples are put into torsion, so you can see that beam there is torqued, and it calculates the shear compliance. And we got the name DHR from Discovery Hybrid Rheometer, which is the piece of equipment that this is run on. And you can see these are very small sample sizes. They're 12.5 by 12.5 millimeters, and it's about 1/100th of a material of an IDT test. So these are very, very small sample sizes, and you can get a lot more tests done with a lot less material. So this is a very attractive proposition. Here are the three different gradations we looked at. You can see the original gradation is the solid black line on the far right, and then we essentially cut that gradation in half and then cut it in half again. And in order to get these gradations, we place the pan under the number 200 sieve for the original gradation, and that's the traditional gradation, or the traditional place for a pan. But then for the finer gradations, we inserted a number 400 sieve, and we also inserted a number 850 sieve. So these are very fine sieves, but we wanted to make sure that those very small particle sizes were the same gradation as the original gradation, just shrunk to a smaller size. And we did this because one of the concerns about using those small torsion bar samples is that you may have large rocks in those samples that could skew the results of the test. So if you shrink the aggregate size, then you won't have those large aggregates that could potentially dominate a test. For our sample fabrication, we were given a mix design that was performed by the emulsifier manufacturer. So using our material, a mix design was performed in order to run these tests. Samples were compacted at 30 gyrations at the optimal asphalt emulsion content and cut with the tile saw, and then they are cured at 60 degrees Celsius for 2 days. Now it's important to note that CIR is often referred to as a semi-bound material, so the samples were often either damaged or destroyed in the cutting process because it didn't quite have the cohesive nature of hot mix asphalt. So we used ice water to cool the saw blade and also the samples so they were a little more brittle, so they were easier to cut, and this worked really well. So some of the first results, looking at the three different testing configurations, you have the IDT, which is the original sample on the left, you have the three-point bend in the center, and the DHR. And you can see here that we used full wrap, we used half wrap, and then we used half class 7. So those are the gradations when we say half wrap and half class 7. And you can see what happened was the DHR lowered all the values, but it shifted it down. So you see the same general trends, but they're just shifted down in stiffness. The IDT and the 3-point bend test had approximately the same magnitude, and they sorted the data in the same way, but you can see that the error bars are much smaller on the IDT. So there's a higher amount of accuracy for the IDT. Now looking here at the creep testing based on the emulsifier, all these tests were at negative 10 degrees Celsius and they used 100% wrap. And you can see here that you have a medium fast, a fast setting, a medium slow, and a slow setting emulsifier. And you can see in general, as the emulsifier speed decreased, the stiffness also decreased. So the faster setting emulsifiers were a little stiffer. And we believe that the emulsion chemistry may have changed the compaction behavior. So based on how quickly the emulsifiers started breaking the asphalt emulsion when it came in contact with the wrap, that would reduce the lubricity of the mixture and make it a little harder to compact. So that was one possible reason for the trend that we see here. And finally, looking at gradation, you can see here that the finer gradation reduces stiffness and it increases the varigradations. And also the finer gradations had a higher surface area. We thought this could potentially be because of poor coating. Now taking a look at the IDT versus the DHR, we simply put all the samples together here. You can see that the stiffness values correlated pretty well. You see those R² values up above 0.95. However, all of the DHR values were lower, and we anticipated that based on the data, but we felt that we could generate correlation factors which could compare the results more directly. And we'll see that here in a minute. When we look at the IDT versus the 3-point bend, these correlations were weaker for the IDT versus the DHR that we just saw. So looking at the IDT versus the DHR, which is the smallest one, we actually saw better correlation than here, the IDT versus the 3-point bend. Another interesting thing is the testing that was done at -30 did not correlate very well, and one of the reasons is because of how brittle the mixture became, and that was especially complicated with those long spans that you saw with the 3-point bending configuration. Now, as mentioned, we did develop some shift values for the DHR to try and get a correlation that fell along the line of equality for the IDT versus the shifted DHR. And you can see here we got the trends close to the match line, but we did see that the lower stiffness values showed a little bit of a higher DHR result, whereas the higher stiffness values showed a little higher IDT. And that is shown by this rotation around the line of equality, where the lower stiffnesses are below the line and the higher stiffnesses are above the line. And these were generated using a shift factor of 2.53. So in conclusion, we do believe that we were able to reduce the CIR sample sizes. We found that the DHR showed the best correlation to the IDT, and you can see a DHR sample sitting next to a full core on the right. The DHR used approximately 1/100th of the material as the IDT, and you can see here that the coefficient of variation for an IDT was 0.192 and for a DHR was 0.186. So these are very nice coefficients of variation within the data collected, which means that they're repeatable and about in the same ballpark for their repeatableness. However, we did need that shift factor to correlate the results between the DHR and the IDT. So in summary, we found that the DHR can be used to estimate creep behavior versus the IDT to reduce the material needs for testing in the laboratory. If you're interested in learning more, this was just a brief summary, but you can find the full paper in the Journal of Testing Evaluation. You can see the DOI link is here and it is also below. So thank you for your time and we appreciate you joining us.